We were doing polynomials. I think this is the fourth or third class, right? So first thing, does anyone have any questions that they have tried and so far in this topic? If you want to ask, I think that can be a good point for us to. It could be something that I asked or did not ask, doesn't matter. Oh, but that was not in the polynomials class, right? Yeah, but let's do it. No problem. So yeah, find the smallest. Yeah, that's a good question. Find the smallest positive integer. And also, I will ask an analogous question for polynomials. Find the smallest degree polynomial in a certain set. That will be similar. Find the smallest positive integer. Positive integer in this set. So, okay. So what is this set? For this S. So let's first fix two concrete numbers and try the problem. You can take 15 times n plus 12 times n, okay, where n and m belong to integers. So these belong to integers. Just to make this more concrete, what kind of things can be there? If you put n and m equal to 1, then you have 27 in this set. If you put n equal to 2, m equal to minus 1, yeah, then you have 30 minus 12, 18 in the set. And so on. I'm not going to write everything. Otherwise, maybe. And in this set, we want to find the smallest positive integer. So first, is the question clear to everyone? Now, Ishana, since you have tried this, because we are going to do the more general version of this, right? Since you would have tried this, can you tell us in this case, if no, is the smallest positive integer? Alex. So let's try for this. Okay, that's okay. Let's try for this then. I'm sure you can do this. We should try this. So we may not be able to prove immediately, but at least what it should be, we should have an idea. Yeah, it should be 3. So does everybody agree that it should be 3? 3 is certainly in the set, right? When you put, I'm just writing 3 next to this. Yeah, so when you put n equal to 1 and m equal to minus 1, you get 3. And so the answer, let me write it 3. Now, can provide some explanation? Anyone? Now they're looking for an explanation. Because we are confident that it should be 3. Positive integers, so 0 is not allowed, otherwise you can always get 0. That's obviously there, right? The difference will get bigger if we increase n and decrease n. But that's not a very good explanation in the sense, because you see, it could be that you can increase n and increase m. I mean, you increase n like a positive and increase m on the negative side, right? And then, you know, it could catch up, something like that. See, why I'm saying this, because like why this increasing and decreasing reasoning is not so accurate is because this way you get 3. But can anybody tell me, is there some other way to get 3 from 15 and 12? some other way to get 3. No, some other NNM which will give you 3. Eight and minus 5. Let's see. Minus 5. $48. So 48 you mean 12 into okay, got it. Yes, right. Yes, absolutely. And this is you got it by guessing, or I don't know, but we know it's not a trick. So Ishana, you know that there is a way to find all solutions. We don't need to know that for this problem, but I'm just saying. And there are many other solutions. So that increasing, decreasing reasoning, not accurate. And obviously it doesn't follow logically in sense. Follows by common sense, but it's not logically also follows. So it's obviously inadequate in that sense also, but we have a clear. Can you give a better explanation? Satya, you think you can get anything less than 3 and positive at the same time? You have 15 and 12. Right. It seems it's not possible. So at least we know that the 3 is the answer, but we just want to prove it. There is a very simple reason why you cannot get less than 3. See, another thing you can notice about the set is anything in the set is a multiple of 3. That's I mean, so far is there. If you can explain that logically, that should be. Yes, right. And so every element in the set is a multiple of 3. Absolutely. That's the more clear explanation, right? Every element of S is a multiple, writing it in words, of 3. So what's the smallest positive multiple? 3. You cannot get less than 3. Yeah. So is it clear? Yeah. So certainly you cannot get less than 3 and positive, because I mean the smallest multiple is 3. But it's also true that you do. Okay, so somebody is typing. Okay, it's okay that you type, but just turn off the volume. Turn off. So the point is that it's a good thing that you actually get 3. You actually get the 3. And now we would like to get into the more serious version of this question. And this one we will not solve completely. Let's see. Now at least. So let's keep A and B positive. Doesn't matter because you can adjust the N and M, negative, so on, positive. And now we want to ask the same question. So again, in this set, what kind of things are there? There is A, there is B. I have given this kind of problem for some reason, and you'll see that over time it can be very helpful. I'm not guaranteeing anything, but at least from my experience, I'm just saying. There is A minus 2B. So I don't know if it will be positive or not, I don't know, but these things are there in the set, right? A plus B, and so on. Answer, at least answer, like if you don't have to provide explanation, what do you think the answer should be? Right? So certainly you cannot get anything less than the HCF, right? Positive in this. But again, this needs a proof. This is not a proof. This is not so obvious, I guess. Okay, for everyone, I don't know. But what I'm asking is number one. Certainly, there is nothing in S which is less than the HCF. Okay, no positive integer which is less than the HCF. Right? So every positive element of S is at least the HCF. Again, for the same reason, right? You take any linear combination A minus 2B. Again, if the HCF is D, then D divides this. And so that's at least D if it is positive. So then what's the missing link? What more do we need to say that HCF is indeed the answer? Well, we need to say that the HCF can be obtained. By some linear combination. Is that right? Then it will become an element of the set. Then it will be in the set. We need, you see that? I was stressed that on the last point, right? That it's a good thing that we actually got this. Here also we need to somehow show, we will not show now, but it's true that you can actually get the HCF. I mean, so maybe Shana, you already know this. This is what we have already proved, right? Given A and B, right? Given A, B, and given D, you can find the solution. You can find N and M, right? We wrote it as X and Y, but we, so Ishana and Nagesh, you also, right? So you know that you can find X and Y such that you get the HCF. Now, I'm not asking you to prove it now, but you can find X and Y so that you do get the HCF. We, how did we prove it? So, yeah, so we some linear combinations, right? We did it in several ways, in fact, earlier, but let's not get into it. So, what to write in explanation is that the GCD, let's say GCD of A comma B can, writing it words, can be obtained as a linear combination. Okay. And in fact, I will suggest the following, but okay, maybe I'll say this in the number theory class, that this is in fact this is actually the better way to define HCF. This is the good, so how can you define HCF? Given two numbers A and B, take the smallest linear combination, smallest positive linear combination you can get out of A and B, and call that the HCF. And that's correct definition by all this that we have done. But we'll pursue that kind of thing in the and also it provides a lot of interesting things actually. So we'll say all that and not now. But this is easy, and we can connect this to the theory of polynomials also. Okay, we can ask similar question polynomials also, and I think we are ready for that. We are ready for that more or less. We have yes. So let me just give the question and not discuss it, and then you guys think, and we will be ready after some time. Mostly, yeah. That's yeah. Ready means what? It depends on how you can get it done. Find the smallest degree polynomial in so we can take any anything, but one must take it carefully. maybe x minus 1 times fx. Okay, so fx is a polynomial, right? Fx, by fx I mean polynomial. And maybe here I can take very similar, right? This was the A and this was the B, and we were taking linear combinations. Now also we are taking linear combinations, but with polynomials. So you can already see this language of linear combinations seems to be unifying. But and so what should I say? I'll just say that fx and gx for us, just fx and gx are polynomials. More accurate things can be said and so on, but for us, good enough. Find the smallest degree polynomial that you can get, but I think this is not a good question because it's already, I mean, x minus 1 is 1 degree. You cannot get smallest, let me just say positive degree. 1 minute. Yeah, I mean, I could say, but that will lead to a few things. So let's not say those that way. Let's just keep it like this, and yeah, x to the 4 minus 1. Note this down, and this is again something that you can just try, right? It is not a very, you can just take polynomials and try, and you would have a guess also. I think. Let's spend some time. So then, so what was it that we were doing in polynomials? Anyone wants to remind us, or if you have some questions, that's better. Maybe ask. No one has. Okay, then I'll continue where I was doing. You note this down. So I think we had, and I always ask myself like this. We had the following questions. I mean, given a fixed degree, and this can drive all sorts of problems and theorems. So it's better, it's good to, given a degree. So let's, for today, let's just take the degree to be 3 degree. Not going into 2 degree because 2 degree is quadratics, and we can discuss it, and it's good, but it's a very standard topic, right? Which you would find in your school topics and so on, which we'll also do. But I don't want to put that polynomials. Let's try to see how the theory can be useful in 3 degree and so on, right? It's not specific to quadratics, is what I said. Okay, let's try to keep 3 degree and try. We already did some quadratic stuff last time. So, given a degree, how many I should say points, but how many input output values determine a unique polynomial? Okay, this was kind of the question we were asking last time. Right? Do you guys agree? So let's begin with an easy case. Let's suppose I told you that P again, P will plot with 3 degree. So let's say that P is a 3 degree polynomial, and let's say that P of 1 equals to P of 2 equals to P of 3. So you don't have to be rigorous. Try to speak freely. Proofs can be done. And let's see. Let's say I told you that at these 4 points, it is vanishing. So find P, or does there exist a P? Yeah. Or say that there doesn't exist. Yes. So it should be the zero polynomial. And so we can see the P doesn't exist, right? So P will be the zero polynomial, which one can write like this. The coefficients will be all zero, no matter how you write, the coefficient is zero. As a function, it will be zero. Same thing. Why? So why should it be the zero polynomial? We need an explanation. Yeah, so by solutions, you mean 3 roots. Okay, and that's a good enough thing. So because it's a standard pattern, we have also stated it and kind of proved it also, that a polynomial of degree 3 will have not more than 3 places where it is 0, not more than 3 roots. Same thing. Yeah. P. And this is not, we don't need to prove this again, because so let's just see, right? That every time, basically, every time you have a root, what does it do? It gives a factorization of P, right? Kind of gives you like this. Because when you divide it by x minus 1, then there is no remainder. That's the thing, right? And so we get some q. But now q becomes a 2 degree. And then again, you get a factorization of q. And then again, but then that's it. But then 4 cannot vanish at 4. Yeah, so that's a standard. That's like a proof that you cannot have 3, cannot have 4. Now, I'm not saying that it will have 3 solutions. I'm saying it will have at most 3 solutions. Some 3-degree polynomials may not have 3 solutions. You guys agree, right? That's an important point, that it may not have thesis. So can you give an example of a 3-degree? So we'll come to this, but can you just give a simple example of a 3-degree polynomial of P having only one root, one solution? Say root, because it's not an equation, so strictly saying solution is not the correct thing. Very interesting topic, adjusting so that we get 3 roots, or kind of introducing a language so that we can say that it has 3 roots in some sense. But as of now, you will get plenty of examples which don't have 3 roots. So can anybody give? Or just x cube, right? Just say x cube. That's the easiest one, right? Yeah, I mean, you're right, but just x cube. I mean, when is it 0? X has to be 0. There is no other way this can be 0, right? Because 2 cube cannot be 0, 3 cube cannot be 0, right? When you multiply two non-zero numbers, it is not 0. In our world, that's the rule that we have from the beginning in number system. So there's no problem. And so polynomial may not have 3 roots. I mean, so far as we are the way we are counting roots may not have, but it has at most. So with that, it's not possible. What about I changed? Is it changing the question? You tell me. Is this possible? So this also we had seen for quadratics that it is not, for quadratics it was kind of not possible. Let's see for cubics what happens. Yeah. Think. So this is what I'll be doing more of. In the class you have to think. That is very important. Because what you do outside, I don't know. So again, this time it's not zeros. This time there is equal to 1. But well, could you not convert this condition to zeros? All right. So this is also not possible, you say. Right. I mean, this should be a zero polynomial. Right? In the sense that, yeah, I think it's correct to say that it is not possible. It's better to say that it is not possible than saying it's zero. Both are, it is certain, but so why? But that's what goes wrong when you try to find a cubic with these properties? That's what we have to. Yes, exactly. And so the let's see, that's the correct thing, and this is a very useful thing, and it's a good trick also, which is used in other sophisticated. Yeah, so it's like when you divide this polynomial with one, with x minus one, the remainder comes out to be one. I mean, that is all that this is saying, right? P of one equal to one is that's what it is saying, that you divide by x minus one and one. But I mean, why do we study roots? Because zero is a special number, right? So just plug in the chart. See, if there was no zero, the number system would not be, I mean, everything would be the same. 0 really creates a difference. That's because the only number which when you multiply with something gives you back 0, gives you back itself. So that's why when you convert it to this polynomial, so what Ishana just said, subtract 1, just the more accurate way to say the same thing is that you take the polynomial px, subtract 1, and then you start getting roots for that. What this condition is saying is that px minus 1 vanishes at 1, right? Px minus 1 vanishes at 2 by the same reason. You see that? I mean, or you can just say, well, yeah, p1 minus 1 is 0. And this is what? This is part of what? You can just say that px minus 1, this polynomial at 1 is 0. There are many ways to just see it in your own way. That you have constructed a polynomial which becomes 0 at some point. It becomes 0 at 1. Right? And that polynomial is px minus 1. So px minus 1 px minus 1 should also be the 3-degree polynomial if p were the 3-degree polynomial. But this again vanishes at 1, 2, 3, 4. At all these points, it is 0, just using a bad note, wrong notation, but understand. But again, same problem. So convert situation to zeros. Remember, this is a very useful trick because that's why we study the zeros of a polynomial. Understanding the zeros of a polynomial gives you the whole polynomial's understanding because it is a simple factorization. I mean, knowing the values at any 4 points gives you full information. For a qubit, knowing the values at any 4 points gives you full information. That information could be not possible, or if possible, it gives you a polynomial, a unique polynomial. That also will show that you get at least one polynomial and you don't get 2 polynomials. Any 4 points does that, but knowing the zeros gives you the polynomial in a very straightforward way by just the factorization. You see the difference. If I told you there are 3 zeros, 1, 2, 3, then you can just say it is x minus 1 times x minus 2 times x minus 3 plus some a, which a fourth value would tell you. It would either tell you that what the value is, or it would tell you that a doesn't exist and so it's not possible. Okay, so converting that information to 0 is what you should look out for. One clear way in which you can proceed. If it doesn't work, you come back and try something else. But that's one clear way in which you can proceed. Remember, that's what we're trying. We're trying to understand the polynomial, which is a function, takes in input, takes as outputs. But we're trying to understand this function via the places where it becomes 0. It's a very interesting thing that knowing just the places at which the function becomes 0 tells you the entire function. There's some sort of rigidity is there, right? So that is, but you draw more graphs, which we are kind of not doing now because you don't want to end up in a mess, kind of many things. So I will see if you guys get comfortable, I'll go faster. But yeah, eventually we will have to go faster. But it's a very interesting thing. Just knowing 4 things or 3 things, it tells you the entire story. What it is at any 5th point, any 6th point. But here, this is the easiest case which we saw of not impossibilities. You know the impossibilities, like the parallel and don't meet and things like that, the impossibilities. Now we can come to more interesting. Slightly turning the difficulty one step at a time so that you all have to participate and try. So let's say that P of 4 is 1. Does there exist a P? Let's see, and then let me say the full thing. Find P. Can there be 2 such P? And all along, it's important that it's 3 degree. The 4th degree, then the story changes. Pragnish did not come. Yeah, I should also not be typing, but just So she sent me. Okay. No, but yeah. So what should that A be? Or let's just to begin with. Let's write this now. So far, it's not a proof that it can exist. So far, because the A has to be set. It's like, what if A is 0? Then there doesn't exist. So what should the A be? So is this like, this is the obvious, this is the natural thing to do. Everybody sees that, right? You know the distinct roots, and so you get these factors. Either you see it as a rule, fine, but you should understand that it comes from that remainder factor theorem applied repeatedly at Euclid's division. What should that A be? That is simple, right? Just put 4 and see, right? This is what, I mean, you know, it would look like this. Sorry, -5, you said? -5, okay. So we take that, and that's probably correct. That's correct, okay. And the good thing is that you could only find one such A. There are no two ways. There's only one way. So no is done. And so if that is done, then is it fine? Please tell me. So I should know. We didn't have to solve equations, right? We didn't have to put, okay, polynomial px is a3 times x3 plus a2 times x2 dot dot dot. Again, you put value of 1, 0, this, solve equations, find those coefficients. We didn't have to do all that because the roots were given. That's a costly thing to do, solving those equations and so on. Whether it would have a solution or not, we don't know so far from what we have studied. So, I mean, logically, kind of should have, and so on. You can reason, but then you don't know. So you try to prove that it has. But then you see, now I will not go into proving this, otherwise you will not end up getting it. Point is that you know that this is true. That you can take any A1, any A2, any A3, any means that they. Okay, so to begin with, let me just say that they are distinct, though they don't have to be. In fact, what needs to be, yeah, so they don't have to be distinct. I mean, no, so they are distinct. So for us, they are distinct. Just a minute. Yeah, but we're not going to. Okay. So let's assume that they're all distinct for us. Okay, otherwise we won't have the full information. And then A4 is another. Like A4 has to obviously be different. Otherwise you can't get 0 and 1 value. And then there is A4. I mean, so you agree that given this, there is. I mean, this all these, yeah, can be found also very easily, and no. So this, I mean, 3 input values for which the output is 0, okay? And the fourth value should be different. Now that also we have seen it has to be different, and it can be anything. I mean, in fact, it doesn't have to be 1, right? It can be anything other than 0. Right? That you also agree, right? Anything that you can imagine you could solve and find the leading coefficient in that condition. So with these 4 input output values for which 3 of them are 0 and the fourth one is not 0, it has to be not 0, we have seen. We can find the unique polynomial. Is this agreed? Yes. Okay. If not, then you should tell me. Say something. Okay. Now we would like to make it slightly more interesting. And so you see, we are getting this theoretical answers and also being able to find the polynomial. Now it gets more interesting. Let's see. So let's again do with numbers. Right, I mean, it's just that if you're just doing this on your own, what's the next thing you would say, right? When the values are different, when you give all different outputs, not 0. Right? So this is something that this is the way I'm not just like, okay, this topic you're learning, I'm saying something, you're answering it, but you also see the way I am trying to develop it. And you can try to follow that approach to learn because there are so many things, right? Most of the maths you have to learn on your own. Remember, most of anything you want to get very good at, you have to learn a lot of most of it on your own. So this is the thing. I am breaking it down to the simplest case we went first, the trivial case, and then the next, and then the next. This way is very, very safe. So let's say this. This is there. Again, the same questions. Yeah? Is there a P? Let's begin with this. So you see, I'm not just taking 4 arbitrary values, I'm taking a pattern. And this is the kind of things you can do in any sort of topic. Yeah? Start with a circle, start with circle in the center, start with circle of radius 1, right? And start with some specific point, specific line and do. It's just that you have to have that patience and energy to do it. So let's try. And Nagesh, so the classes you missed, I have put recordings for most of them. You can just have a quick if you can see. Yes, I think before that also were you there? No, I think in the GCD class you were not there, right? That happened on Tuesday. Yeah, so that also you were not. I don't know. Were you there? that ax plus by. Yeah, no, after that, I think. Yeah, that is there, but after that also the simple divisibility and GCD. I don't know. So, but I think you want, so I mean, this question that find the minimum value of that set, those kind of questions I had asked in that class. And I think you were not there in that. Yeah. So it will be there in one of those we checked in the list. Yeah. Last few videos. Maybe I should put the dates also. I mean, it's mostly for you guys only. So it's not okay, come on, let's do this question. So today we have to do this one. Induction class yesterday was a very basic one since Satya was the only one. So I went extremely slowly and we tried to, but in one thing and we went in very rigorous detail. So it was an easy class relatively. So this one, again, as I have suggested, so what could you do? You could assume that there is a cubic and get equations. That's one way which we did not do, but let's write. So this is a polynomial. Then you say, okay, putting 1 gives me 1. Putting 2, this is obviously impractical for us to really solve. Though there are efficient ways to solve this, but 2 and so on. So you have 4 equations, 4 variables. Hopefully there will be a solution. And so that's there. So that is not what we will do. So then what is the other way? I mean, so at least the hunch is that there should be. So should be. But so can we again, using the strategy earlier, can we again convert it to a 0 kind of condition where some polynomial is vanishing? Convert this to roots of something. So px, when you divide it by x minus 1, you get 1. When you divide it by x minus 2, you get 2. I mean, so this is a different quotient. And I mean, it's just the unnecessary thing I'm writing, I think. You can already convert this to a sort of 0 information, right? In the sense of something vanishing. So, I mean, look, p1 minus 1 is 0. Isn't this p2 minus 2 is 0? p3 minus 3 is 0. What is this telling you? It's suggesting that we should consider px minus x. Right? Px minus x has the roots 1, 2, 3, and 4. Right? That's the nature of this condition, p2 minus 2, p3 minus 3. So px minus x, if you consider, it's not a surprising, it's not some trick, right? It's a natural thing, kind of. It's a little tricky, but you see, px minus x vanishes at 3, vanishes at 4. For this information neatly gets packed into this polynomial. But then what does it mean? It means that this polynomial, whatever this is, some gx, it vanishes at 4 values. It's a cubic. What can we say? We can say that this is identically 0. This is 0 polynomial. This is this, right? It's the 0 polynomial. So always, everywhere 0 at all points. And so what do we get? We get px is x. That's what we are getting. So is there a, first of all, is this clear so far? Because we've done a little bit of a trick. It's the same idea of considering related polynomials so that all this gets back, all this information can be stated in terms of roots. Considering px minus x in this case is natural. But do you see that? Yes, Ishana and Sukhdev. X is a no, so x is not a cube, x is just x. I didn't understand. Is there? Yes, yes. So then px is not a 3-degree polynomial. It turns out that it has to be linear. You're right, yes. So if you want the answer, in that case, there is no. Correct. Yeah, no, that's correct. Yeah. Right. So see, the way it's kind of is, it's kind of we are assuming that we should just say that px is at most 3 degree, but then we are getting that it cannot be 3, it has to be 1 degree. Right? So strictly speaking, the answer should be no. Right? But there is a polynomial, and it's the most obvious one, right? So yeah, but px equals to x works, and it is only one, and is the, so this is what it is. Yes, as one would have guessed, right? But one shouldn't be too quick to guess. There are, you will see more as you do, but we have established rigorously that px equals x is the only possibility, and so there is no cubic. There is a non-zero polynomial, but there is no cubic. So the point to take away from here is what we are kind of getting towards is, given 4 distinct inputs and any 4 distinct outputs, we are getting towards the not got there. Given any 4 distinct inputs and any 4 distinct outputs, there is a non-zero polynomial. So given any 4 distinct inputs and 4 distinct or non-distinct, there is a polynomial. It could be 0, it could be linear, and we don't know, but there will be a polynomial. But more importantly, there are no 2 polynomials, there is at most 1. If the degree is 3 and 4 input output informations are given, then we don't get 2 polynomials, we seem to always get only 1 polynomial. It could be 0, it could be 2 degree, 1 degree, so in that case you may say no polynomial, but there are no 2 solutions. So it completely determines the polynomial. That's the point I'm trying to make. And then it may not be cubic, so you can say it doesn't exist, but there is no 2 polynomials. But we are getting towards that. Okay? Now, what should you do for homework? You can try to take, that's up to you what you want to do. You can take cubes here and try. You can try different things. You can take four powers and try. Right? It's up to you. So you try different things and see, or you just take some other number. If p of 1 equal to 10, p of 2 equal to 2, p of something, take some arbitrary values and try and see. Those are the things that you have to try. Okay. Yes. So I'm not giving any particular homework this time. There's a question I gave in the beginning. There is this arbitrary question sort of here. Yes, there's no need to. You just and just see if you have it. But just try. You can try from anywhere you want. But challenges and thrills is a one reference that I have, and exercise 10.4 is what we said. Yes, please try. For those who are trying challenges and thrills, is not mandatory. Exercise 10.5, okay, where it's just some calculations. You have to just try to find GCD and LCM of polynomials, which is something that you would have practiced high in your school syllabus also, right? And so you can try those few problems that are there. Calculate. It's good to calculate a few. If you get bored, don't do it, stop it, but try as many as you can. And try these problems. And if you have some other sources, please search, try if you have other books. But we have our own questions to answer, and this is where we are going. This will lead to what is called Lagrange interpolation, which is a very important theorem in this topic. And standard, if you see any Olympiad handout or anything, this will be there. And they're getting towards that, but not in like one fast. Okay, so I'll stopping. Okay. Thank you. Bye. Please come up with interesting questions next time. It will be much more. Yeah.